Venus has just encountered something it had not faced for billions of years, and we almost missed it. On November 23rd, 2025, while global attention remained focused on Martian events from a month earlier, an interstellar comet delivered into Venus's atmosphere something that, by all expectations, simply should not have been there. And this is what makes the situation impossible to ignore. Material originating from the dark regions beyond our solar system, from depths where Venus has never reached, managed to survive inside Venus's sulfuric acid clouds. Pause for a moment and consider that. Venus is the planet where Soviet landers melted within hours. A world where surface temperatures exceed molten lead, where pressure is comparable to being submerged a kilometer underwater, and where clouds consist of concentrated battery acid. And yet, this very planet has just received organic molecules, water, and refined metals from an object that drifted through interstellar space for roughly 10 billion years. Against all expectations, instead of being instantly destroyed, part of this material survived. More than that, it began reacting. It is actively altering the chemistry of Venus's atmosphere, triggering processes whose nature scientists are only beginning to comprehend. This is not science fiction. This is November 2025. This is happening right now. In the upper layers of Venus's atmosphere, an intense and rapid transformation of matter is underway. Matter that arrived only weeks ago from beyond the solar system. Clouds that had remained chemically stable for billions of years now contain molecules that never belonged to Venus's natural chemistry. Unlike Mars, where interstellar material simply settles on the surface, waiting for future excavation, Venus responds immediately. Its chemistry is aggressive, dynamic, and reactive. It eagerly processes foreign material, creating entirely new reaction pathways. But before we can understand what all this means, we must first clarify what exactly happened on November 23rd. The interstellar comet, 3IATLAS, the same object that passed Mars on October 22nd, made a second close approach, this time to an inner planet. The distance was about 2/3 of an astronomical unit, roughly 97 million kilometers, close enough for Venus's gravity to capture part of the comet's gaseous envelope, close enough for the diffuse cloud of gas and dust surrounding the comet's nucleus to intersect with the upper layers of Venus's atmosphere. Close enough for an exchange of material to occur between the interstellar visitor and a planet that had not received external chemistry for eons. Timing played a far more critical role than it might seem. When 3IATLAS passed Mars earlier, Mars presented a thin atmosphere and a cold, largely inert surface. Material fell, settled, and essentially froze in place, awaiting future processes. Venus, however, is a completely different case. Venus's atmosphere is over 90 times denser than Earth's. Winds in the upper layers reach speeds of around 100 meters per second, driving a phenomenon known as global superrotation. Venus's cloud layer circles the entire planet in just 4 Earth days. Temperatures within the cloud layer range from roughly 0 degrees C down to 60 degrees C, cold enough for chemical reactions to occur, yet warm enough for them to proceed actively. Most importantly, these clouds contain sulfuric acid, extraordinarily aggressive, yet paradoxically capable of preserving certain organic molecules that no one expected to find there. When 3IATLAS passed Venus, its coma extended across millions of kilometers. The comet was releasing significant quantities of material, more than 120 tons of water per hour, hydrogen cyanide at roughly 80 grams per second, carbon monoxide in comparable amounts, and, most unexpectedly, a pronounced enrichment of nickel relative to iron. The mechanism behind this separation remains unclear. Venus's gravity captured only a fraction of this material, far from all of it. Most was swept away into space or dispersed by the solar wind. But what Venus did capture was enough. Models suggest that Venus intercepted between 3 and 10% of the material that passed nearby. The geometry of the encounter played a decisive role. Mars experienced a grazing interaction with limited contact time. Venus, by contrast, was positioned closer to the core of the comet's outflow. As a result, Venus intercepted not only the diffuse outer layers of the coma, but also denser regions closer to the nucleus, receiving more water, hydrogen cyanide, organic compounds, and metals than Mars. Observational coverage, however, was limited. The primary data came from Japan's Akatsuki orbiter. NASA and ESA spacecraft were positioned elsewhere along their orbits and could not observe Venus in detail at the time. Akatsuki's data has reached Earth and is currently being analyzed, but unlike the Martian encounter, it lacks multiple independent confirmations. As a result, interpretation relies heavily on modeling and on our understanding of how Venus's atmosphere should respond. One thing, however, is certain. 3IATLAS passed close enough for material transfer to occur. The comet was actively shedding matter, and Venus's dense, gravitationally bound atmosphere inevitably captured a measurable fraction of it. The first molecular collisions and decelerations occurred in the upper atmosphere, from which the material entered Venus's circulation system. What remains unknown is the precise concentrations involved, the exact chemical pathways the molecules followed within the clouds, and how the system responded during the first hours and days. But the essential point is this. The event broke the long-standing isolation of Venusian chemistry. For billions of years, Venus's atmosphere functioned as a closed chemical system. Everything within its clouds originated from Venus itself, from its geology, its volcanic emissions, and its photochemistry. Nothing arrived from the outside. Every molecule, sooner or later, returned to the same cycles. Reactions repeated along identical pathways for eons, stable, predictable, isolated, until November 23rd. The substances delivered by 3IATLAS were not in equilibrium with Venusian chemistry. They were foreign, reactive, and carried chemical information from regions Venus had not encountered since its formation. Hydrogen cyanide, for example, is almost entirely absent from Venus under natural conditions. Its appearance represents genuinely new chemistry. Water vapor, present on Venus only in trace amounts, arrived in noticeably higher local concentrations. Refined nickel, which has no place in Venus's clouds at all, entered the mixture, possibly dissolving into droplets of sulfuric acid. And these substances did not remain static. Within hours, atmospheric circulation began distributing them around the planet and across different altitudes. Within days, photochemistry initiated bond breaking, radical formation, and entirely new reaction chains. Within weeks, all cloud layers became involved in processing the foreign material. Venus's atmosphere, stable for billions of years, was disturbed. The system reacted. And as of late November 2025, that reaction is still ongoing. The question is no longer whether Venus has changed. It has. The real questions are, what exactly is Venus doing with this new chemistry? How long will the changes persist? And will interactions between sulfuric acid clouds and interstellar molecules produce something truly unexpected? To understand what 3IATLAS disrupted, We must first understand what Venus's atmosphere actually is, not the simplified caricature often presented. Yes, it is hot. Yes, it is acidic. But its chemistry is far more complex than the image of a uniform hellscape suggests. And it is precisely this complexity that makes the introduction of external material so significant. Venus's atmosphere is not a single layer of sulfuric acid and carbon dioxide. It is a vertically stratified system composed of distinct chemical zones, each existing under its own temperatures, pressures, and compositions. One useful analogy is a layered ocean. Surface waters differ from the thermocline, which in turn differs from the deep ocean. Venus's atmosphere behaves in much the same way. When material from 3IATLAS entered it, it did not encounter a uniform environment, but several chemical regimes at once, each responding differently. Let us begin at the top, where cometary material first made contact. The upper cloud layer, extending roughly from 60 to 70 kilometers in altitude, consists of sulfuric acid droplets, with concentrations between about 50 and 75%. Temperatures here range from roughly 0 degrees C down to 20 degrees C. This is cold enough for water vapor to condense into ice crystals, and cold enough for certain organic molecules to remain stable longer before photochemical destruction sets in. Pressure in this region is low, close to 1 Earth atmosphere. Molecules therefore travel longer distances between collisions, slowing chemical reaction rates and extending molecular lifetimes. This upper layer is also the most dynamically mixed region of Venus's atmosphere. Wind systems driven by thermal and pressure gradients create circulation that encircles the entire planet every 4 Earth days. Any material entering here is rapidly spread globally. Below this lies the middle cloud layer, between approximately 50 and 60 kilometers altitude. Here, sulfuric acid concentrations increase to 75–90%, while temperatures drop further, to about 20 degrees C to 40 degrees C. This is where Venus's most visible atmospheric features form: streaks, waves, and vortices observed by orbiting spacecraft. Chemistry in this layer is denser and more aggressive. Molecules that survived the upper layer now encounter far more concentrated acid. Some are destroyed. Others are transformed into new compounds. Still others dissolve into acid droplets, transitioning from the gas phase into the liquid phase. Lower still lies the bottom cloud layer, roughly 45 to 50 kilometers above the surface. Acid concentrations remain extremely high, and temperatures fall to 40 degrees C to 60 degrees C. Pressure approaches 1 Earth atmosphere. Conditions here are hostile to most organic chemistry. Molecules that reach this region are either fully destroyed or converted into stable end products. This lower layer functions as a chemical terminal. Substances are either incorporated into precipitation cycles, later evaporating and rising again, or broken down into components that re-enter long-established atmospheric loops. Beneath all 3 cloud layers, from the surface up to about 45 kilometers, lies what is often called the clear atmosphere, though the term is misleading. Visibility is severely limited by aerosols and haze. Carbon dioxide and nitrogen dominate, and temperature rises steadily with depth. At the surface, temperatures exceed 460 degrees, where chemistry resembles industrial furnaces rather than atmospheric processes. No cometary material survives there. This vertical structure is crucial. When material from 3IATLAS reached Venus, different substances ended up in different layers. Light molecules such as water vapor and hydrogen cyanide penetrated deeper before being fully slowed. Heavier particles, nickel-bearing grains, silicates, mineral dust, decelerated more quickly and remained in the upper layers, settling only gradually. Each substance found its own chemical niche. Water entering the upper layers interacted with diluted acid and cold temperatures, condensing into mixed droplets and releasing heat. Hydrogen cyanide entering the middle layer dissolved into more concentrated acid and began hydrolyzing, forming ammonia and formic acid through reactions involving water within acid droplets. Nickel-bearing particles reacted with sulfuric acid at all levels, forming nickel sulfates that dissolved into the droplets. Each pathway produced its own products and its own consequences. All of this unfolded inside a system that had remained essentially unchanged for billions of years. Venus's atmosphere operates like a conveyor belt. Sulfur dioxide rises from below or forms via photochemistry. Upper layers convert it into sulfuric acid. Acid forms clouds. Droplets grow, sink, evaporate in the heat, and return to the gas phase as sulfur dioxide. A closed loop, no external deliveries, no water-rich asteroids, no organic-bearing comets, no metal-rich dust. Until now. Suddenly, molecules appeared that Venus had not processed in geological memory. Hydrogen cyanide concentrations rose above background levels. Water vapor increased locally where cometary material was captured. Nickel compounds, utterly alien to Venus's clouds, began circulating in the upper atmosphere. These are non-equilibrium components. They do not belong to Venus's standard chemical cycles because they came from elsewhere. And when foreign chemistry enters an ancient, stable system, the system responds. It reacts, attempting either to incorporate the new substances or to destroy them back into familiar forms. Sulfuric acid clouds, which define Venus's appearance, are now participating in unfamiliar reactions. Water mixed with acid locally reduces acidity, making the environment less aggressive. Hydrogen cyanide, converting into ammonia, introduces alkaline chemistry into an overwhelmingly acidic atmosphere. Ammonia neutralizes acid, forming ammonium sulfate, a stable salt that can persist for weeks. Nickel ions grant cloud droplets catalytic properties they never previously possessed. Organic molecules produced from hydrogen cyanide breakdown can accumulate in regions where photochemistry has not yet destroyed them. This is no longer the atmosphere of early November 2025. It is a slightly altered chemical system, displaced from equilibrium and exploring reaction pathways that never occurred under normal Venusian conditions. To understand the true significance of what reached Venus on November 23rd, we must examine the chemistry of the delivered material with precision. Details matter here. By early November 2025, comet 3IATLAS had already passed its perihelion on October 29th and had begun moving back toward the outer solar system. But moving away from the Sun does not mean inactivity. After perihelion, comets often remain active for weeks or even months as residual solar heat continues to drive sublimation from the nucleus. The outgassed material remained largely the same as in previous months. Water, hydrogen cyanide, carbon monoxide, and the unexpected component that makes this event unique, refined nickel, separated from iron by processes that resemble industrial chemistry. Water production in early November remained substantial, on the order of 120–130 tons per hour. While this was slightly below the October peak of around 140 tons per hour, it still represented an enormous flow of material. For comparison, a fully loaded passenger aircraft weighs roughly 180 tons. The comet was ejecting nearly that mass in water alone every 90 minutes. Most of this water dispersed into space, spreading through the comet's coma and tail. But when a comet passes sufficiently close to a planet with strong gravity and a dense atmosphere, part of that material is inevitably captured. The efficiency of Venus's capture depended on several parameters: relative velocities, encounter geometry, coma density at Venus's distance, and the effective interaction cross-section of the atmosphere. Current models estimate a capture efficiency between 3 and 10%. Applying those numbers to the water flux suggests that Venus received between roughly 3 and 12 tons of water during the hours of peak interaction. At first glance, this may not sound dramatic, given that Venus's atmosphere already contains several thousand tons of water vapor. But the critical factor is not total quantity. It is distribution. This water did not arrive evenly. It was delivered into specific atmospheric regions where the geometry of the encounter placed Venus directly within the comet's outgassing flow. Local concentrations were therefore high enough to measurably alter humidity, cloud droplet composition, and reaction rates that depend sensitively on the presence of water. Hydrogen cyanide followed a similar but chemically far more consequential path. Throughout October, the comet's hydrogen cyanide production increased dramatically. By perihelion, extrapolations placed emission rates between roughly 75 and 100 grams per second, an extraordinary value. Most comets release only a few grams per second of HCN even at peak activity. This unusually high output likely reflects the comet's interstellar origin and its long exposure to extreme temperature gradients after billions of years in deep space. By November 3rd, during the Venus encounter, hydrogen cyanide emission had stabilized at approximately 80-85 grams per second. Over the 4 to 6 hour window of maximum gravitational and atmospheric capture, Venus likely received between 1.2 and 1.8 kilograms of hydrogen cyanide. Hydrogen cyanide is not a normal component of Venus's atmosphere. Only trace amounts are produced through photochemical processes. Receiving kilograms of it represents a genuine chemical novelty. Unlike water, which Venus's atmosphere, though depleted, is still chemically adapted to process, hydrogen cyanide introduces reaction pathways that Venus does not normally employ. HCN is a precursor to amino acids. It is a building block of nucleotides. It is one of the key molecular markers used in assessments of prebiotic chemistry. And it arrived at Venus in concentrations sufficient to briefly create localized chemical environments before photochemistry destroyed it. Carbon monoxide was released at similar rates, roughly 60-70 grams per second, according to ground-based spectroscopy. This implies Venus captured on the order of 0.9 to 1.7 kilograms of CO. Carbon monoxide already exists in Venus's atmosphere at about 20 parts per million. However, the comet created localized zones of elevated concentration, which is chemically important, particularly for catalytic reactions. Now to the most unusual component, refined nickel. Spectroscopy showed that nickel was being emitted preferentially separated from iron. This anomaly points to chemical processes within the comet's nucleus, resembling industrial carbonyl formation, where nickel forms volatile nickel-carbonyl compounds while iron remains non-volatile. By November 3rd, nickel emission rates were estimated at roughly 3 to 4.5 grams per second, slightly below October peaks. Over the interaction window, this yields between 50 and 110 grams of nickel captured by Venus. The mass is tiny. The chemical significance is enormous. Nickel is a catalyst. It accelerates reactions without being consumed. Even trace amounts can radically alter the dynamics of a chemical system. Once inside Venus's sulfuric acid cloud droplets, nickel does not remain metallic. It reacts immediately, forming nickel sulfate, a soluble compound that integrates into the liquid phase of the droplets. These droplets acquire new catalytic properties. Reactions that would normally proceed extremely slowly now accelerate. Nickel catalyzes, for example, the water-gas shift reaction. Carbon monoxide plus water forming carbon dioxide and hydrogen. It also catalyzes Fischer-Tropsch type reactions, which extend carbon chains and form more complex organic molecules. And now, for the first time, Venus's sulfuric acid clouds contain a catalyst that enables such chemistry. Beyond these major components, the comet delivered a wide spectrum of minor substances. Organic molecules synthesized in the coma, sulfur-bearing compounds, silicate dust, mineral grains, and trace metals. Spectroscopy detects only the most abundant species, so the full chemical inventory remains unknown. But comets are chemically rich objects. Everything ejected from the nucleus becomes part of the delivery package. Venus did not receive just water and hydrogen cyanide. It received a complex chemical cocktail, dozens or hundreds of molecular species, all of which began interacting with Venusian atmospheric chemistry the moment they were captured. This represents true chemical novelty. For billions of years, Venus's atmosphere received no external chemical input. The substances now circulating in its upper clouds are genuinely alien. They did not originate from Venus's surface, nor are they products of its own photochemistry. They came from an object formed in another star system, one that wandered through interstellar space for unimaginable spans of time before briefly intersecting Venus's orbit. The chemistry carried by that object encodes information about cometary processes, interstellar environments, and chemical pathways active during the comet's formation billions of years ago. Now that chemistry is interacting with Venus, transformed by sulfuric acid and solar radiation, producing compounds that blend interstellar heritage with Venusian processing. By late November 2025, the initial delivery phase had ended. The material is now fully integrated into Venus's atmospheric circulation. It reacts, breaks down, recombines, creating a transient chemical state that Venus has not experienced in all of its geological history. And the data documenting these transformations exist. They were recorded during the encounter and transmitted to Earth. They are now undergoing calibration and analysis. We are in the interval between observation and publication, the phase where raw data becomes understanding. That understanding will reveal how Venus's atmospheric chemistry responded to this unexpected interstellar gift. To understand where the cometary material now resides within Venus's atmosphere, we must understand how Venus captures incoming matter and redistributes it afterward. This process is fundamentally different from impacts on solid surfaces. Venus's atmosphere is not a static shell. It is a fluid, continuously moving system that transports material both vertically and horizontally. When matter from 3IATLAS entered Venus's sphere of influence, it did not plunge straight downward. Instead, it was gradually slowed by gravity and atmospheric drag, captured into atmospheric flows, and immediately carried away from its initial entry point. This redistribution determines where concentrations are highest today, where chemical reactions are most active, and where spacecraft instruments are most likely to detect changes. Venus's gravitational sphere of influence, the region where its gravity dominates over the Sun's, extends roughly 1 million kilometers from the planet. This is an enormous volume of space. Although the comet passed at a distance of about 97 million kilometers, particles from its coma still entered this region. At that distance, the coma was relatively diffuse. The densest gas and dust lie closer to the comet's nucleus. But even sparse material becomes significant when interacting with Venus's dense atmosphere. Cometary outgassing is directional. Material is ejected primarily from the sunlit side of the nucleus, where heating is strongest. This creates a cone-shaped flow of gas and dust trailing the comet away from the sun. The densest part of this flow lies along the cone's axis. Venus's position relative to this outflow cone during the November 23rd encounter determined how much material its atmosphere intercepted. Had Venus passed directly through the densest region, capture efficiency would have been higher. Had it grazed the edge, lower. Orbital mechanics placed Venus in a favorable, though not optimal position, not at the core of the flow, but close enough that concentrations remained substantial. This geometry likely explains why Venus captured more material per unit area than Mars, despite Mars having a closer encounter earlier. Once particles entered Venus's upper atmosphere, the thermosphere above roughly 100 kilometers, deceleration began immediately. High-velocity molecules collided with atmospheric gases, losing kinetic energy with each impact. Light molecules, such as water vapor and hydrogen cyanide, slowed more gradually and penetrated deeper before being fully captured. Heavier particles, dust grains, mineral fragments, nickel-bearing compounds, lost momentum more quickly and remained at higher altitudes. This naturally produced stratification, different substances accumulating at different heights based on mass and aerodynamic behavior. By the time material reached the cloud layers between about 45 and 70 kilometers, it had lost nearly all of its original velocity. From that point onward, it no longer followed an independent trajectory. It moved at the speed of the local winds. And Venus's winds are extraordinary. Despite Venus's extremely slow rotation, one Venusian day lasts over 240 Earth days. Its upper atmosphere completes a full circumnavigation of the planet in just 4 Earth days. This phenomenon, known as superrotation, drives winds at cloud level, reaching speeds of around 100 meters per second. As a result, no material remains localized for long. Within hours, it is carried hundreds or thousands of kilometers horizontally. But Venus's circulation is not purely horizontal. The atmosphere also exhibits strong vertical circulation, resembling Hadley cells on Earth. Warm air rises near the equator, and the subsolar point flows poleward at high altitude, descends at higher latitudes, and returns equatorward at lower levels. Combined with superrotation, this creates a fully three-dimensional mixing system. Material introduced at one location is spread across latitude, longitude, and altitude simultaneously. Within days to weeks, cometary substances are distributed across much of the upper atmosphere, though not uniformly. Regions of descending airflow can accumulate higher concentrations as material is compressed and retained there. Polar regions, where atmospheric dynamics are more complex and partially isolated, may trap localized pockets of enhanced abundance. The location of initial entry on November 23rd played a critical role. Orbital geometry indicates that material entered from the hemisphere experiencing late-morning local solar time. This region was sunlit, actively heated, and located within rising airflow. As a result, incoming material was rapidly lofted into the superrotating upper layers, from which it spread globally. Temperature within the cloud layers is a key controlling factor. In the upper cloud layer, where temperatures range from roughly 0 degrees C to 20 degrees C, conditions allow water to exist as ice crystals and permit organic molecules to survive longer before photochemical destruction. In this relatively cold region, material can persist for weeks before being transported into warmer or more strongly irradiated zones. The middle cloud layer is colder still, approximately 20 degrees Celsius to 40 degrees Celsius, but contains the highest concentrations of sulfuric acid. Chemistry here is especially aggressive. Many molecules that survive the upper layer are destroyed or transformed in this region. Photochemistry begins immediately once molecules are exposed to solar ultraviolet radiation in the upper atmosphere. UV photons break chemical bonds, producing highly reactive radicals. Water molecules dissociate into hydrogen and oxygen. Hydrogen cyanide breaks into cyanide radicals and hydrogen. But photodissociation does not mean immediate disappearance. The products of these reactions are often as chemically significant as the original molecules. They can recombine with other atmospheric components, forming entirely new compounds. Hydrogen released from water can react with carbon dioxide to form formic acid. Cyanide radicals can interact with ammonia-derived compounds to produce more complex nitrogen-bearing organics. Photochemistry initiates a cascade of transformations that ultimately breaks down the cometary material, but the intermediate products of that cascade become part of Venus's atmospheric chemistry during the process. Global atmospheric mixing requires on the order of 1 to 2 weeks. That is the time needed for substances introduced at a single location to spread through the upper atmosphere under the combined effects of superrotation and vertical circulation. By late November 2025, several weeks after the encounter, the initial localized concentrations had largely dispersed. The substances were present throughout Venus's upper atmosphere in low but detectable amounts. Some regions, however, likely retained higher concentrations. Descending flow zones at higher latitudes and polar regions may still contain enhanced levels, preserved by atmospheric dynamics. Detecting these changes requires targeted spacecraft observations focused on specific regions and chemical species. The instruments aboard the Akatsuki spacecraft, designed to study Venus's atmospheric composition and dynamics, are capable of measuring trace gases and cloud properties. If data analysis reveals elevated levels of water vapor, hydrogen cyanide, or nickel compounds in predicted regions, it will confirm the capture and redistribution models. If not, it will imply either lower capture efficiency or faster destruction and dispersion than expected. Either outcome provides critical insight into how Venus's atmosphere responds to external chemical input. The key point is this: the measurements exist. The encounter was observed, the data were recorded. We are now in the interval between observation and publication, the moment when raw measurements are transformed into scientific understanding. And that understanding will show, in detail, how Venus's atmospheric chemistry responded to material delivered by an interstellar comet. At this point, everything we thought we knew about Venus begins to unravel. For decades, the scientific narrative was simple and seemingly unquestionable. Venus was sterile. Any organic material entering its atmosphere would be instantly destroyed by sulfuric acid clouds, intense ultraviolet radiation, and extreme conditions. Venus was treated as the ultimate counterexample to habitability, a warning of what happens when planetary climates spiral out of control. Life could not arise there. Complex chemistry could not persist there. Venus was chemically dead. But that picture is no longer fully accurate. In March 2024, a study published in Astrobiology fundamentally altered our understanding of what Venus's atmosphere is capable of sustaining. Researchers tested 20 biogenic amino acids, the very molecules used to build proteins in all known terrestrial life, in sulfuric acid solutions designed to mimic Venusian cloud chemistry. The acid concentrations, temperatures, and exposure times matched conditions in Venus's upper and middle cloud layers. The prevailing assumption was straightforward. Most, if not all, amino acids would rapidly degrade or be destroyed. That expectation was wrong. Out of the 20 amino acids tested, 11 showed complete stability, no reaction, no degradation. They remained intact in sulfuric acid concentrations that were expected to annihilate them. 8 more amino acids remained stable even after partial chemical modification. They transformed into closely related compounds rather than breaking down into unrecognizable fragments. Only 1 amino acid out of 20 showed significant instability. Consider what this means. 19 out of 20 amino acids either survive unchanged or persist in recognizable modified forms within sulfuric acid under Venus cloud conditions. These are not exotic molecules. They are fundamental building blocks of life, and they can persist in Venus's clouds. This finding directly contradicts the long-standing assumption that sulfuric acid instantly sterilizes all organic chemistry. It does not. Sulfuric acid is selective. It aggressively attacks certain molecular structures while leaving others largely intact. And among the molecules that survive are precisely the types delivered to Venus by cometary chemistry. Hydrogen cyanide, delivered by 3IATLAS on November 23rd, is a well-known precursor to amino acids and other organic building blocks. Its breakdown products include the very molecules shown to be stable in sulfuric acid cloud conditions. This changes the interpretation of the event entirely. Hydrogen cyanide did not simply arrive and vanish. It arrived and initiated a cascade of transformations, each step potentially producing stable or semi-stable compounds that can persist long enough to participate in further chemistry. When hydrogen cyanide dissolves in the diluted sulfuric acid of Venus's upper clouds, it hydrates and reacts with water, breaking down into ammonia and formic acid. Ammonia is a base. In an environment dominated by strong acid, bases locally neutralize acidity. This creates microenvironments inside cloud droplets where acidity is reduced, pH is higher, and chemical pathways become accessible that would be impossible in pure sulfuric acid. These partially neutralized droplets become sites of particularly active organic chemistry. Sulfuric acid droplets transform into microscopic chemical reactors. Each droplet contains a complex mixture: sulfuric acid, water, dissolved cometary organic molecules, ammonia from hydrogen cyanide breakdown, formic acid, and trace amounts of nickel compounds. The chemistry inside these droplets is far from equilibrium. Solar radiation continuously supplies energy. Droplets move vertically through the atmosphere, experiencing changing temperatures and pressures. Each droplet is isolated from others, a self-contained reaction vessel, suspended in the clouds. This creates an enormous parallel chemical experiment. Billions upon billions of droplets simultaneously explore different reaction pathways. Most will produce nothing remarkable, random combinations leading nowhere. But some will, by chance, follow pathways toward greater molecular complexity. Short peptides formed from linked amino acids, nitrogen-bearing organic molecules, lipid-like compounds derived from organic acids. This is not life. It is not biology. But it is complex chemistry, structured, non-random, and far beyond simple precursors. This is exactly the type of chemistry astrobiologists study when investigating how life's building blocks might emerge from non-biological processes, whether on early Earth or on other worlds. And this chemistry is not hypothetical. It is happening now, in Venus's clouds, as a direct consequence of the November 23rd encounter. For several weeks already, sulfuric acid droplets enriched with cometary organic material have been circulating through Venus's upper atmosphere. They react, rearrange, and potentially form increasingly complex structures. At the same time, photochemistry continues to work toward their eventual destruction. Ultraviolet radiation constantly breaks chemical bonds, producing radicals. But complete photochemical destruction takes time, weeks to months, not seconds. During that window, organic chemistry remains active. This makes the situation even more remarkable. For years, Venus's clouds have been considered a potential, though highly speculative, habitat for hypothetical microbial life. Not because sulfuric acid is biologically friendly, but because certain physical conditions align unexpectedly well. Temperatures in the upper clouds are moderate. Liquid water exists within acid droplets. Sunlight provides energy. Clouds are stable enough to keep particles suspended indefinitely. The strongest objection was always chemical. What would such microbes consume? Venus's atmosphere contains almost no organic material. Any hypothetical life would need to synthesize everything from carbon dioxide and nitrogen, an energetically extreme challenge. But if Venus periodically receives organic material from comets, meteorites, and interplanetary dust, that constraint weakens dramatically. And now, 3IATLAS has delivered a substantial pulse of exactly such material: hydrogen cyanide, amino acid precursors, organic fragments. If hypothetical microbes exist in Venus's clouds, unlikely but not impossible. They have just received a food supply. If they do not exist, far more probable, then the chemistry that could one day lead to such systems has just been seeded. Does this mean life will suddenly arise in Venus's clouds? Of course not. The gap between complex organic chemistry and true biology is vast. It involves countless additional steps and conditions. But that gap is now slightly smaller than it was before November 23rd. Venus's clouds are now exploring a region of chemical possibility they normally never reach, enabled by an interstellar visitor. And the implications extend far beyond Venus. If sulfuric acid clouds can support prebiotic organic chemistry, if molecules can survive, react, and grow more complex in environments once thought sterile, then our understanding of where life-related chemistry can occur expands dramatically. Acidic environments on other planets become less categorically hostile. Atmospheric chemistry becomes a far more interesting arena for prebiotic processes. The number of places in the universe where complex chemistry might emerge increases. All because sulfuric acid turned out not to be a universal destroyer, but a selective one. It destroys some structures and preserves others, and among those preserved are many of the fundamental building blocks required for life. This is not coincidence. This is chemistry. And chemistry, it turns out, is far more flexible and creative than our simplified models suggested. Right now, Venus's atmosphere is demonstrating that creativity, processing interstellar material, entering reaction pathways unseen for billions of years, and potentially generating levels of complexity we will not fully understand until observational data are analyzed and published in the coming months. There is one element that makes the current state of Venus's atmospheric chemistry truly unprecedented: catalytic nickel. When refined nickel delivered by 3IATLAS entered Venus's sulfuric acid clouds, it did not arrive as a passive contaminant. Nickel is chemically active. It is one of the most effective natural catalysts known. Its appearance introduced a capability that Venus's atmosphere had never possessed before: the ability to accelerate specific reactions so dramatically that processes once effectively impossible could suddenly occur. To understand what nickel can do in Venus's clouds, we must first understand catalysis itself. A chemical reaction can be imagined as a journey over a mountain. Reactants sit in one valley, products in another. Without a catalyst, the reaction must climb a high energy barrier. At Venusian temperatures, many reactions are thermodynamically allowed, but kinetically frozen. They proceed so slowly as to be irrelevant. A catalyst provides an alternative pathway, a tunnel through the mountain. The energy barrier is lowered, and the reaction proceeds rapidly. The catalyst does not change whether a reaction is energetically favorable. It changes how fast equilibrium is reached. In systems where reactions should occur but practically do not, catalysts transform the impossible into the feasible. Nickel catalyzes several reactions of profound importance in Venus's atmosphere. The most significant is the water-gas shift reaction: carbon monoxide plus water, carbon dioxide plus hydrogen. Venus's atmosphere now contains elevated carbon monoxide delivered by the comet, and water exists within cloud droplets. Under normal Venusian conditions, these molecules could coexist indefinitely without reacting. The activation energy is too high. But in the presence of nickel, the reaction becomes viable. Nickel provides surfaces or coordination sites where carbon monoxide and water can adsorb close together, react, and release products. The consequences are subtle but far-reaching. Carbon dioxide is denser than carbon monoxide. Its formation alters local buoyancy and pressure profiles within cloud droplets. Hydrogen, by contrast, is extraordinarily light. It is the only molecule capable of fully escaping Venus's gravitational field if it reaches sufficiently high altitudes. The loss of hydrogen represents a minute reduction in atmospheric mass, negligible per reaction, but potentially measurable if the process becomes widespread. More importantly, hydrogen is highly reactive. Before escaping, it can participate in reduction reactions, donating electrons to other molecules. In the presence of catalysts, sulfuric acid itself can be partially reduced, forming sulfur dioxide and water. Organic molecules can be chemically modified through reduction, producing structures with very different properties. Nickel also catalyzes Fischer-Tropsch-type reactions, in which carbon monoxide and hydrogen combine to form longer carbon chains and more complex organic molecules. In industrial settings, Fischer-Tropsch chemistry requires high temperatures and pressures, but catalysts drastically lower those requirements. Venus's clouds are not ideal reactors, but they now contain nickel, hydrogen, carbon monoxide, and localized zones of higher concentration and compression. In certain droplets, especially in regions of descending airflow where pressure and temperature temporarily increase, these reactions may proceed at non-negligible rates. The products would be organic molecules more complex than those delivered by the comet itself. Nickel also catalyzes general condensation and restructuring reactions among organic compounds. If amino acids coexist with nickel ions inside droplets, nickel can facilitate peptide bond formation, linking amino acids into short peptide chains. If nucleotide precursors are present, nickel can catalyze their condensation into longer structures. This is not speculative fantasy. On Earth, Many biological enzymes rely on metal ions, including nickel, in their active sites to accelerate precisely these kinds of reactions. Life did not invent metal catalysis. It adopted it from chemistry. In Venus's cloud droplets, nickel plays a similar role, not biologically, but chemically. Each droplet becomes a catalytic microreactor. Within it, sulfuric acid, water, ammonia, organic molecules, and nickel interact under constant energy input from sunlight. Temperature fluctuates as droplets rise and fall. Photochemistry continuously generates radicals that feed into new pathways. The system is far from equilibrium. Most droplets will produce nothing of lasting significance. But given the sheer number of droplets, trillions upon trillions, rare pathways become statistically inevitable. Some droplets will explore reaction routes leading to increased molecular complexity. Not life, not cells, but chemistry, approaching the boundary, where organization begins to matter. And all of this is happening in an environment that, until recently, was assumed to instantly annihilate organic chemistry. The presence of nickel fundamentally changes that picture. It means Venus's clouds are no longer merely destructive. They are conditionally constructive. They can dismantle molecules, but they can also build. This does not mean Venus is becoming alive, but it does mean Venus is temporarily hosting chemistry that resembles, in structure and behavior, the early prebiotic chemistry thought to precede life on Earth. And this chemistry was triggered not by slow internal evolution, but by a sudden external perturbation, the arrival of material from an interstellar comet. That makes this event unique not only for Venus, but for planetary science as a whole. We are witnessing in real time how a long isolated planetary atmosphere responds when exposed to truly alien chemistry. Chemistry shaped in another star system under conditions radically different from those of our own. The response is not simple destruction. It is transformation. Venus's atmosphere is exploring chemical pathways it has not accessed for billions of years. Some of those pathways may be fleeting, others may persist for months or longer. All of them provide insight into the flexibility of planetary chemistry. And that insight forces us to rethink some of our deepest assumptions. Not just about Venus, but about where complex chemistry, and perhaps eventually life, might emerge in the universe. When all the pieces are assembled, the event of November 23, 2025, emerges as something far more profound than a simple cometary flyby. For billions of years, Venus existed in chemical isolation. Its atmosphere evolved inwardly, recycling the same molecules through the same pathways, locked into equilibrium. External chemistry simply did not arrive in any meaningful way. That isolation has now been broken. An interstellar object, formed around another star, shaped by unfamiliar environments, and preserved through immense spans of time, briefly intersected Venus's orbit and delivered a pulse of foreign chemistry into a closed planetary system. Water, hydrogen cyanide, carbon monoxide, metals, and complex organics entered an atmosphere that had not processed such material since its earliest history. And Venus did not merely destroy it. Instead, the atmosphere reacted. Sulfuric acid clouds, once assumed to be purely corrosive and sterilizing, revealed a far more nuanced role. They dissolved, transformed, buffered, and redistributed the incoming chemistry. Water altered acidity. Hydrogen cyanide generated ammonia and organic precursors. Nickel introduced catalysis, unlocking reaction pathways that were previously inaccessible. What emerged was not chaos, but exploration. Venus's atmosphere began probing regions of chemical possibility it had not accessed for billions of years. It became temporarily a laboratory for non-equilibrium chemistry, driven by sunlight, circulation, and catalytic surfaces inside microscopic droplets. This chemistry is transient. Photochemistry will continue to break bonds. Circulation will dilute concentrations. Eventually, the system will relax back toward equilibrium. But eventually is not immediately. For weeks to months, Venus's clouds exist in a chemically altered state, one where complex organic molecules can form, persist, and interact in ways previously thought impossible. This does not imply life. It does not imply biology. But it does imply prebiotic relevance. And that matters. Because it tells us something fundamental about planets. It tells us that atmospheres are not merely passive envelopes. They are dynamic chemical systems, capable of sudden transformation when exposed to new inputs. It tells us that acidity alone does not preclude complexity. It tells us that catalysis can radically reshape what chemistry is possible, even in extreme environments. Most importantly, it expands our conception of where meaningful chemistry can occur. If Venus's clouds, acidic, irradiated, and hostile by terrestrial standards, can temporarily host complex organic chemistry, then the range of environments capable of supporting prebiotic processes is wider than we assumed. Acidic atmospheres on other planets and exoplanets become less categorically sterile. Interactions between atmospheres and transient external material, comets, dust, interstellar visitors, become central to planetary evolution, not peripheral curiosities. This event also reframes interstellar objects themselves. They are not just messengers from other star systems. They are carriers of chemistry, mobile reservoirs of molecular history. When they intersect planetary systems, they do more than pass through. They interact, they perturb, they seed, and sometimes briefly they awaken dormant chemical potential. Right now, the data from this encounter exist. They are being analyzed. When published, they will quantify how much material was captured, how it was redistributed, and which chemical signatures persist. Those results will not tell us that Venus is alive, but they may tell us something just as important, that the boundary between sterile and chemically interesting is far thinner than we believed. Venus, long regarded as a dead world, has reminded us that chemistry does not need comfort to be creative. It only needs opportunity. And on November 23, 2025, Venus received one